So actually also the lab assignment number 2 will be posted on the Blackboard. So I believe it is automatic. It was automatically posted on the maybe 1 a.m. tomorrow, I believe. So actually, in the lab assignment number 2, you are requested to design data path elements using system variable. So in chapter 4, we learned about the data paths of the single cycle processor, and then data path elements includes some hardware components in the data path. So which means that it's instruction memory, register file, ALU, and data memory. So in this lab assignment number 2, you are requested to design individual hardware component. Okay? It's called the data path element. So actually, you are requested to design instruction memory, register file, ALU, and data memory. But I slightly changed the architecture of this single cycle processor, because actually in a textbook, this single cycle processor only supports the 7 instructions like load, store, add, sub, or, and repeat instructions. But in this design lab, you are requested to your processor needs to support more instructions, like immediate instructions, and then also another branch instruction like BQ, BNE, BLT, and BDE. Okay. So actually, in order to support more instructions, we need to modify ALU. Actually, other components are the same. The instruction memory just to store the instruction. So instruction memory is the same, and then register file is also the same, because register file also just to store the register values. Okay, and data memory is the same. It's the memory. Okay, it is not influenced by some instruction, but the ALU should be modified in order to support the more instructions. But I just provide some table. So actually, you can find the ALU OP here. Okay, so actually we learned how the ALU OP signal is determined. So if the ALU OP signal is 0, then this ALU supports the memory instruction like load or store instruction, and then ALU function is the add. And then if the ALU OP is 0, 1, then which means that it's the branch instruction, then ALU needs to perform sub instruction. And then this is the ALU control signal. And then other R-type or I-type arithmetic or logic instruction. The ALU OP signal is 1, 0. Then the required control signals are determined by some different instructions. So we need to check the function 3 or function 7, but this is just ALU. So you don't need to consider about the function 3 or function 7. So actually, the ALU receives only ALU OP and then ALU control signal. And then based on the ALU OP and actually ALU control signals. Okay. So based on the ALU control signals, then this ALU needs to support some different operations. Okay, so let's see the content. So I briefly explain about the design lab number 2. Okay, so this is the instruction fetch engine of the single cycle processor. So as you can see, so you can find that the instruction memory is here. The instruction memory has 2 ports. So one input port So PC is, oh, this will be 32. Okay. So the PC is given to the read address port of the instruction memory. And then if the PC is given, then we can read the instruction from the instruction memory. So this is the, so actually I also provide the skeleton code of the this hardware component. The skeleton code means that I just provide the input and output ports of the hardware component. So as you can see, oh, if we see that this instruction memory, then you can find two ports, right? The address port and instruction port. So I define the address port here, and then also I define the out. Out is the D out. Here represent the data out. Okay. But the PC is the 32-bit, okay, and then with the also the actually the size of a single instruction is the 4 byte, okay. So which means that in order to support the full range of this program counter, then instruction memory needs to have 2 to 30 entries, right? So actually, because the one single instruction is the 4 byte, and using this program counter, the 32-bit program counter, the instruction memory needs to have the 2 to 30 entries. So, but it's very large. So actually, we cannot design this large instruction memory. So I restrict the size of this instruction memory. So which means that this instruction memory just has the 1024 entries. Okay. So which means that this instruction memory can store up to 2024 instructions. And then the size of a single instruction is the 4 byte. And then the number of entries is 1024, which means the size of this instruction memory is the 1024 multiplied 4. This is the 4 kilobyte. Okay, you can calculate the size of the instruction, size of the memory like this. But which means that we need this address port is just has the 10-bit width because the number of entries is 1024. Okay. And then register file. Also, this is the skeleton code of the register file for the reg file. And then register width is the 32 because it's the we are learning about the IV32I. And then also the width of a general purpose register is defined in instruction set architecture, the 32-bit. So these are the some ports in the register file. So register file has the two read register port and then one write register port, and then one write data, and then two read the data out. And then also we need the read write control signal. But if you see the skeleton code of this system very low, then you can find the clock signal. So it is because, so also I write some comments inside of the skeleton code. So please read my comments in this skeleton code. So why do we need the clock signal? It is because like this, add x1, x1, x1. So if we do not have, if this register does not have any clock signal, so which means that the write update should be done at the positive of the clock. But if there is no clock signal in the register file, what will happen? So if this instruction is executed, then this instruction is the data from the register number 1, and then the destination register is also register number 1. So x1 equal x1 plus x1. Then, but the behavior model of the very low, and then this is just the combinational logic. Then if the input is changed, then outputs are also changing. So I already explained in the combinational logic, the output is just determined by input values, right? But what's the problem? If this instruction is executed, x1 equal x1 plus x1, so which means that x1 is changing, right? Which means this value is changing. Input values are changing, which means this register just also performs the x1 plus x1, and then x1 is updated or changed. X1 plus x1 is also performed and then change it again and again. So what is this? This is the infinite loop, because input values are changed, and then these input values are changed again and again and again by the destination of this add instruction. So we cannot, the infinite loop is generated, and then we need to avoid this case. So that's why our system Verilog design has the clock signal, and then is the register write. The register write is done only at the rising edge of the clock. Can cannot avoid this infinite loop. Okay, so you can read my comments in the skeleton code. Okay. And then data memory also has the 1024 entries. And then we assume that size of a single entry is the 4 byte. Okay, so because this processor just supports the load word and then store word. Okay, so these are input and output ports of the data memory. So I define the input and output ports of this data memory. Also, you can find the clock signal here. So actually, it's the similar reason. So not to avoid the infinite loop in the data memory, and then we may also need this clock signal. But another reason is that so you can find this clock signal, and then I also kindly write the comment like the write is just for the write operation. But actually, for the write operation, we need the clock signal. Okay. If not, then the infinite loop can be generated. Also, another reason is that if the write is done without clock signal, then this design will generate latch. And then if the latches are generated by system Verilog, our IT design, then this is the bug. Okay. So usually the write is done. Write is triggered by clock signal. Okay. So and so this data memory has the two control signals, and the mem write and then mem read control signal. Okay. So which means that we will also use this mem write or mem read. And then ALU control. So and then as I explained, only the ALU is changed by the, supported instruction. So which means that in a textbook, the single-sided processor only supports the 7 instructions, but in this design, our single-sided processor needs to support more instructions. But and then as I explained, I just provide this table. So you can write, or you can design the ALU based on this table. Okay, so actually, so this is the block diagram of the ALU. So ALU receives the 2 input operands, right? And then ALU receives the ALU control signal. This is the 4-bit control signal. What is this control signal? It's equivalent to the ALU control. And then based on the ALU control, the ALU supports the add operation and sub operation and or exclusive or operation. Okay. So and then as I mentioned, the ALU receives the 2 input operands like here and here. And then based on the ALU control signal, ALU just generates the result. Okay. For example, if the ALU control signal is the 0010, then ALU needs to perform the in 1 plus in 2, and then this is the actually result, right? And then if the ALU control signal is 0110 or 0110, the ALU control for 0110, then the result should be in 1 minus in 2, right? So based on the ALU control signal, then result should be changing. Okay. But so if you read the skeleton code of the ALU, then you can, I believe. So actually, in the skeleton code, you can find the if statement. So it's very similar to the switch statement of C. And you can, I believe you can figure out how to generate the result of the ALU. Also, this ALU has the 2 other output ports called the 0 and sign. Actually, 0 is the same to the 0 of the ALU in the textbook, right? So when is the 0 becomes the 1? So this 0 out of the ALU becomes 1 when result equal 0, right? Then 0 becomes 1, right? Otherwise, 0 is 0. Okay, so it's the same to the definition in the textbook. Then how about the sign bit? Why do we need sign bit? So sign just check the sign bit MSC change the MSB of the result, right? So why do we need the sign bit? So why do we need the 0 bit? Because in order to support the branch instruction, like the BQ, actually it was the BQ in the textbook. So actually the original single-sided processor in the textbook supports only BQ. So which means that we need to check the 0 of the result. So if the result is the 0, then so we perform the sub instruction. Then if the A minus B equals 0, then which means that A equals B. Or if the 0 is 1, then the condition of the branch in BQ is 2. That's why we need BQ output from the ALU. No, 0 output from the ALU, right? Then why sign? So actually, our single cycle processor for this design then needs to support the BQ, PME, PLT, and PGE. Actually, BQ and PME is the same. So we can use the 0 bit, right? So which means it's equivalent, it's the not equivalent. And how about the PLT and PGE? So actually, we need to check the magnitude of the two occurrence. So it means that if A minus B is less than 0, which means it's the A is less than B, right? So that's why we need to check the sign bit of the A minus B to support BLT and BGE, right? That's why our new ALU has the additional sign bit region. Okay. So in our lab assignment number 2, then you are requested to design 4 data path elements. So actually, and then as I mentioned, I provide the skeleton code for these hardware elements, the data path element. Also, I provide the test bench code for validator. Okay, so you can find the PB underbar for the IMEM CPP. So this is the test bench for the IMEM. So actually, in a first lab assignment, then you are requested to install validator. So you are requested to design a simple gate logic using validator. Okay, and then so you can verify your design, like this data path element design using provided test bench. Okay, so this is some instruction, so command for verifying the instruction memory using the validator test bench. Okay. So also, if you have any question and if you struggles to write the code, then you can stop by PA's office, or you can also stop by my office during the office hours, right? So please make use of PA's. Also, you can stop by my office by appointment. So you can post any questions on the PS chat. Okay. So I hope everyone can complete the second lab assignment. Okay. So any questions? Well, yeah. So we can use the other simulator. Actually, it's a verification tool. So this simulator is called the verification tool. 그냥 한국어로 좀 하긴 할게요. 그 모델심이나 아니면은 그런 다른 뭐 NCC 같은 verification 툴은 사실은 프리 툴은 안 돼요. 저는 사실은 돈을 주고 사야 되는 툴이긴 한데, 얘네들은 그냥 좀 복잡하게 RTL 시뮬레이션을 수행을 합니다. 그러니까 이제 베릴로그 같은 경우가 제가 이 코스에서는 이제 베릴로그를 뭐 제가 이제 가르칠 수가 없잖아요. 뭐 컴퓨터 아키텍처 코스니까. 베릴로그는 사실은 C처럼 하나의 프로그래밍 랭귀지고요. 어떤 식으로 이제 시그널들이 이제 읽혀지고 또 실행되는지 다 룰이 있어요. 시뮬레이터, 그러니까 베리피케이션 툴 이런 것들은 다 그런 베릴로그의 룰에 맞춰가지고 시뮬레이션을 수행을 하고요. 그때는 사실은 이런 타이밍 정도. 그러니까 이건 하드웨어잖아요. 하드웨어이기 때문에 우리가 타임을 고려를 해야 돼요. 사실 이런 베릴로그나 서스텐 베릴로그는 이런 타임 정보에 따라서 시그널이 변하는 것을 잘 시뮬레이션 하기 위해서 설계가 된 프로그래밍 랭귀지. 그렇기 때문에 이제 모델심이나 아니면은 이런 여러 툴들은 많이 쓰신 상용 툴인데요. 돈 주고 사야 되면. 그런 이제 스튜던트는 뭐 공짜로 쓸 수 있습니다. 뭐 그렇긴 하지만, 근데 이제 덩치도 크고, 그 다음에 그냥 좀 복잡한 툴이에요. 근데 이제 베릴레이터라는 툴은 이 시스템 베릴로그나 이제 베릴로그를 C로 컴파일을 해줘요. 그러니까는 여기는 사실은 타이밍 정보가 하나도 없죠. 우리가 이제 C 코드나 이런 거를 이제 뭐 파이썬으로 뭔가 코드를 짜면은 거기에는 타이밍 정보는 아무것도 안 나오잖아요. 그냥 한 라인 한 라인 수행이 될 뿐이지. 그런데 이제 베릴레이터라는 툴은 우리가 이제 그런 타이밍 정보를 다 약간 TD라고 하는 그러니까 한 어떤 클락 사이클에 어떻게 이제 신호가 이제 수행이 되는지만 고려를 해가지고 얘를 C 코드로 아니면 C++로 바꿔줍니다. 그 다음에 이제 실행을 시켜주는 거예요. 그러니까 사실 장점이 뭐냐면은 엄청 빨라요. 그냥 기존의 이제 모델심이나 이런 NC즘 같은 경우에는 타이밍 정보를 다 고려를 해줘야 하기 때문에 시뮬레이터가 엄청나게 느립니다. 엄청나게 시간이 오래 걸리니까 디자인이 크면 클수록 우리가 이제 이런 베릴로그 시뮬레이션을 하려면은 굉장히 오랜 시간이 이제 걸리고 또 이제 뭐 툴도 굉장히 복잡하고요. 그런 게 있는데 베릴레이터라는 거는 그 우리 시스템 베릴로그를 C 모델로 바꿔주기 때문에 굉장히 빠르고 C가 빠르잖아요. C가 굉장히 빠르기 때문에 굉장히 이제 빠르게 할 수 있는 대신 시간이라는 개념은 다르죠. 시간이라는 개념이 어떤 퀵이라는 근데 퀵이라는 약간 이제 클락 개념으로 이제 바뀌는 거죠. 근데 이제 이게 별 문제가 안 될 수가 있는 게 어차피 이제 우리가 이제 디지털 그 디자인을 다루기 때문에 디지털 디자인들은 다 클락에 분기돼가지고 한다라고 했잖아요. 그러니까 그냥 최종적인 뭐 어떤 결과, 최종적인 리절트만 보는 데 있어서는 그냥 픽처럼 최종적인 그냥 결과만 체크를 할 때는 베릴로이터로 빠르게 돌리는 것도 장점이 있는 거죠. 그렇기 때문에 사실 이 수업에서는 제가 베릴레이터는 걸 쓰고 있는 거고요. 그리고 뭐 또 한 가지 말씀은 여러분들이 이제 뭐 애플이나 이제 그런 ARM 프로세서를 쓴 툴도 사실 애플이 있거든요. 애플이 요새 이제 그 ARM 프로세서를 써서 자기 랩탑 만들지 않나요? 잘 팔리고 있고. 근데 이제 문제는 이제 모델 심리나 이런 툴들이 안 돌아가요. 그러니까는 이거 실습하려면은 또 여러분들 많이 애플 컴퓨터 가지고 있는데 모델심 돌릴 수가 없으니까 하라고 할 수도 없고. 근데 이제 베릴레이터 같은 경우에는 그 애플에서도 제공을 그러니까 애플 어차피 이거는 컴파일에서 만들면 되는 거기 때문에 그 애플 칩에서도 돌아갑니다. M1, M2에서 돌아가기 때문에 그래서 제가 베릴레이터로 하고 있는 거예요. 사실 그게 좀 커요. 그 전에는 모델심이나 이런 걸로 좀 하라고 했는데 이게 애플이 M1, M2를 발표를 하면서 안 돌아간대요, 학생들이. 그래서 베릴레이터로 바꿨죠. 그 장점이 있습니다. 어쨌든 베릴레이터는 아까 말했듯이 굉장히 빠르게 시뮬레이션 할 수가 있고, 그 다음에 이거는 이제 오픈 소스이기 때문에 우리가 이제 자유롭게 쓸 수가 있습니다. So, okay. Oh, we have only 15 minutes. Okay. So, okay. So, uh, in this time, so I will explain about the pipeline, the concept of the pipeline. So actually, in the previous class before our midterm exam, we learned about the single cycle processor. And then I hope you remember the last page of the is single cycle processor design. So last slide, where is the last slide? So if you see the last slide of the single cycle processor chapter, then you can find that, oh, longest delay determines clock period, which is same to our last question of the midterm exam. And then what is the critical path? Critical path is the load instruction. Okay. So actually this longest delay determines the clock period. And then as I explained, the performance is determined by execution time. And this is the IC, CPI, and then PC, which means that clock period also determines the performance of the processor. And that's the problem. But if we see the hardware components of the single cycle processor, then we can find that a certain hardware is only used during a certain step. So which means that in the instruction fetch step, our processor, single cycle processor, just uses the instruction memory, right? Only access the instruction memory. But during the other steps, like the ID, execution, memory, and write back, this instruction memory is not used. Okay. So problem is that, oh, because of this longest delay, then the clock period is determined by this longest delay. But if we only focus on the a single data path element, we can find that instruction memory is only used during this period, right? And then during other time here, this instruction memory is not used, but during this long time, this hardware is just in the idle state. It's not used. And then this is the waste of resources, right? Even though this hardware is not used for a long time, but because of this longest delay of the single cycle processor, the clock period is determined by this critical delay, critical path, the longest delay of the many hardware components. Okay, so this is the performance issue. So then what is the pipeline? So I will explain using the analogy. So this slide shows the analogy of the pipeline. So let us assume that this is actually a very famous analogy in the pipeline. So let us assume that we are doing some laundry. So let us assume that we are using the laundry service. Okay, and then which means that for this laundry service, we need to use first the washing machine, and then the second, then we need to use the dryer, is a conjugate, and then we need to also fold our clothing, and then we need to pack up folded clothing to the closet. So let us assume that these are 4 required steps for laundry service. Okay. So then these are the tasks, so kind of some clothing. So for one task, for a single task, then we require these 4 steps. So which means that then also it takes time for each step. So which means for this task, that this task requires the 4 different steps, and then in order to complete the entire steps, then it takes 2 hours, so 30 minutes per step, right here. And then after this task complete, then we can start the next task, right? Task B. So this task starts at this time, so 8 p.m., and then it takes 2 hours and it completes at 10 p.m. And then we can start the other task and then other task like this. So what's the problem? The problem is that, so let us assume that these are hardware components. So during this 30 minutes, and then for this task A, we use this hardware resource, washing machine. And then in order to use so while using this dryer, but for during the another 30 minutes, this washing machine is not used to. Okay? And then also for another time period, these hardware resources are not used. So that is the waste of hardware resources. So which means that even though, so we already know that, not to complete this task, we require 4 steps, but in each step, other hardware resources are not used at all. So this is the waste of hardware resources. Also, doing these 4 tasks, it takes very long time because before completing the 4 more tasks, the next task cannot be started. Okay? Then how can we organize this task? So this is the pipelining idea. So task A starts at 6 p.m. and then it completes using this washing machine at 6:30. Then, washing machine is available, and then this washing machine can be used by next task. And then this is possible, right? Because this washing machine is not used by task A anymore. Okay? Task A is, so at the same time, at the same time slot, task A is using dryer, and then task B can use washing machine at the same time because the hardware resources are separated, hardware components are separated, right? And then C, during this 30-minute period, so we can use all 3 steps for different tasks. And then during the next 30-minute period, we can also use the other hardware components, other steps for different tasks. So what's the benefit? The first benefit is that if we see the usage of this washing machine, then washing machines are used continuously. Okay, so which means that the hardware resource is not wasted. Okay? We can make use of hardware resources without any idle state. Also, another benefit is if we just see the execution time of these 4 tasks, and in order to complete the 4 tasks, then this machine, this process takes how many time? 6 hours, right? No, 8 hours. But if we use the pipeline scheme, this scheme is called the pipelining. If we use the pipeline scheme, then we can complete these 4 tasks in 3 and 5 hours, 3.5 hours, right? So what is the other benefit? Performance. Performance can be improved. This is because we can make use of these hardware resources without any idle state. Okay? So what is the speed up? Speed up is the 2.3. Okay. So that is the benefit of the pipeline. Also, this pipeline can be applied to the processor architecture. Why? As I explained, the way in order to execute a single instruction, our processor requires 5 steps: instruction fetch, ID, execution, memory, and write back. And then we already learned that. So when we learned about the data path in the single cycle processor, actually only a certain hardware components are used for only a certain step of a single cycle processor. For example, in the instruction fetch, we use the instruction memory only. And then for the ID stage, we use the register file. But register files read port. Okay. Then in the execution step, we only use ALU, the memory. We use the data memory, and then the write back. We use the register file, but it's only write port. So for each step, our single cycle processor use the hardware separated hardware component. So as I explained, if we just design a processor like the single cycle processor, instruction memory only used during this time period, and then for this long time period, instruction memory is in idle state. It's not used. That is the waste of hardware resources. Also, because of the longest critical path, the long critical path of the single cycle processor, the clock period is also increased. Then performance is degraded. That is bad for the performance of the processor. So like this analogy of the pipelining, we can split each required step of this processor design. Then we can design the pipelining of this required processor. Okay? So we will learn how to organize the pipelining of the required processor in the next class. Okay. And then this is actually the pipelining is a very important topic in this course. So I hope everyone can understand this pipelining of the processor architecture. Okay. So any questions? Okay. Thank you for your attention. And see you in the next class. 감사합니다.